Hello, this is my presentation of the research paper I wrote this term, Automatic Detection of Audio Deepfakes Through Stylometric and Spectral Features. I'm Philip Jones. So the basic problem that we're trying to solve here is that deepfaked audio is getting better and better. It can almost with perfect accuracy imitate someone's voice so that you can't tell if a statement is actually coming from them or if it's coming from a deepfaked model that someone trained on their voice. There are several services which can simplify this process greatly. Services like Descript, which is a commercial service with proprietary technology, and also the primary source for most of what I have in this presentation. There's Python Project Deepfake, which is an open source attempt at this, but is rather hard to configure and requires a lot of work to get a quality product from. And Google and also Facebook have their own voice emulators, which can be used for the same purpose. So it's very easy to create one of these deepfakes nowadays. These can run with as little as 5 seconds of audio data. They can create a model of the person's voice and what they sound like, and they can do any text-to-speech task that a normal text-to-speech generator can. So this, of course, causes a number of problems surrounding privacy and trust. If there's a public figure and they make a statement that sounds like their voice, we can no longer immediately know whether that is them or whether that's someone entirely different faking their voice. It also enables a wide variety of scams. Say you're calling a bank in an attempt to make a deposit, but in fact what appears to be you is someone deepfaking your voice and mocking your credentials in order to get access to your banking information. So we need a solution which can find the inconsistencies in these near-perfect deep-faked waveforms, and it would be great if it could classify in real time so that it were possible to run the analysis as you speak. So in order to do this, I created a dataset to test on. I used the service Descript to generate some deepfakes. As previously mentioned, Descript is a multimedia presentation company. They have an AI product called Overdub, which is a voice generation software that's backed by AI that can generate some very convincing audio. During the demonstration later, I'll show you exactly what that audio sounds like. So to train one of these models, I collected audio data of participants. They were each of them reading a 10-minute long clip of classic literature. I submitted this 10-minute clip to the service Descript. About 12 hours later, they returned to me with a voice model that I could use for any text-to-speech task. So I generated some text-to-speech based off of classic literature, things like Dracula, Peter Pan. All the sources are enumerated in my paper itself. I took that data, I split both the real and the fake into 15-second sections for use in the training of my neural net. I normalized the amplitude of the waveform to make sure that certain samples weren't overrepresented or we weren't picking up signals that didn't have any real relevance. And I got a transcription of the corpus that I was having the person or the deepfake model read so that I could use that for stylometric analysis. So I used a number of features in order to determine aspects of the waveform of the corpus and try and determine if this is a deepfake. The first class that I use is stylometric. So I'm looking at how this speaker normally speaks as opposed to how they're speaking now, if what the possible deepfake is saying is actually in line with what the person would say. So the metrics I use for this are things like type token ratio. I use mean word length, mean sentence length, median sentence length, mean paragraph length, and how many punctuation marks and ifs and buts are in every 1,000 tokens. I use another class of features as well in an attempt to look at the waveform of the deepfake itself as opposed to its content and see if there are any small artifacts or things that wouldn't be in a normal human voice. So I use a particular set of coefficients called the Mel frequency cepstral coefficients. These are a set of 20 features that are often used for natural speech recognition. They've been written about in a number of publications. I use things like spectral bandwidth, spectral centroids, and roll-off, all of which encode different aspects of the waveform. And I use the average of these across a 15-second sample to give me a measurement of different characteristics of each waveform. So in order to take in these features and predict deepfakes, I created a deep neural network, just a basic one, none of the fancy variants like CNN or LSTM. So this is classifying into two categories, whether it is fake audio or whether it is real audio. The hidden layers are 5 layers of 64 densely connected neurons. I trained this network on batches of 5 audio samples combined with stylometric features from the associated corpuses of the samples. All these neurons use hyperbolic tangent as their activation function, and the final neuron classifies, as I said, between a fake or a real document. All right, so let me show you this data set, and you can listen to the difference between the real audio and what Descript is able to fake. So let's start with the real audio of one of the participants, reading a documentary, I think, from March of the Penguins.
There were 1.5 billion people on Earth. Now, over 6 billion crowd our fragile planet. But even so, there are still places barely touched by humanity.
Alright, so that was the real audio. Now I'll show you what the model trained off of that person's voice was able to generate.
I stuffed a shirt or two into my old carpet bag, tucked it under my arm, and started for Cape Horn in the Pacific. Quitting the good city of Old Monjado, I duly arrived in New Bedford.
As you can see, despite some slight inconsistencies in timing, it sounds exactly like the person themselves, to a point where you would very much struggle to determine if it was or wasn't the person, as just a layperson's analysis. So, I'll show you what we're looking at in the code that I wrote in order to handle this. So the code begins truly here. So the first thing I do is I look through all the directories of my data set and I look for all my audio samples. I load them into memory. If I've already extracted the features in a previous run, I can cache the features, so I don't have to calculate them every time. The spectral features do take a few minutes to extract because it's going through an enormous amount of audio data. In this next section, I normalize the features within the range from the minimum to maximum value for that feature. I split them into 3 sets. My training set, which is 60% of the total samples, of which there are about 253 in total. So 60% of that is training, 20% of that is validation, and 20% of that is test. So that is split into 3 NumPy arrays. I define my network structure here. So you can see it has the dense layers in the center with the tanh activation function, the final predictive neuron at the end, and then an input which is appropriate for the shape of the number of features that are being input. I have some metrics with which the network trains itself, and here is where I actually fit the model on the training data. In order to extract the features that I need for this, I have 2 auxiliary files. Spectral.py uses the Librosa library for audio processing to extract these features from my audio sample, and stylometry.py, which just goes through the corpus and extracts any features that I've demarcated. Things like the tokens per thousands for punctuation, and if but, mean sentence length, like I discussed previously. Alright, so we can have a demonstration of the training in progress. It only takes a few seconds to run, so it's possible at the moment. So you can see it booting up the network down here and loading up some things from TensorFlow. Alright, and it's already trained on the 2 epochs that were necessary. So we can look at the training results here. On the first epoch, it was able to reach 73% binary accuracy, and slightly better on the validation set, probably just through luck. On the second epoch, it does significantly better on the training set, 93, on the validation, 96, and then finally on the test set, which was not used for either of the other 2 operations of audio samples, it's able to achieve 97% accuracy for prediction. I can get slightly better results if I train it for more epochs, but the results kind of plateau at this point. So now that we're finished with that demonstration, I can discuss the experimental results. So I tested this on 3 different feature sets in order to demonstrate that the combined feature set does achieve a higher level of accuracy and is more precise than either of the sub-feature sets alone. So I tested it on stylometric features only looking at the corpus of the original and the corpus of the deepfake and looking for stylometric differences between the two. And that achieved a pretty good level of average accuracy, average 91% accurate on this rather small data set. I looked at spectral features only, trying to extract those waveform clues, which was able to achieve 88% total accuracy. And then the combined accuracy on those 2 epochs was about what we saw in the demonstration at 97%, with some variance over a few tests. You can also see how the accuracy is consistently better over my 5 validation runs using 5-fold cross-validation. So this shows that the combination of these stylometric and spectral features can enable us to detect deepfakes more robustly and more independently of how good the deepfake technology actually is, because with stylometric features we can determine based on the content of what's being said whether this could be a deepfake. So there are a few next steps, improvements I would like to make to this project. I'd like to use a different network structure. I'd like to use an LSTM or recurrent neural network structure. This will allow me to extract time feature or time domain features from my waveforms and allow me to see the variations in small local spaces within those waveforms. I'd like to expand my data set out significantly. Getting data was one of the hardest tasks in this because it takes a very long time to process and clean all the data and make sure that it's in the correct form for my network to ingest. But I think that an investment in gathering more samples would show that this was more robust and would yield us a better predictive network. I'd like to test this on any external data sets that I could find. I haven't found any yet, but I could dig deeper into that and see if there's any validation I could do on a test set that I didn't create. All right, so that's the end of my presentation. I hope you enjoyed, and thank you for listening.